Hi. Solving equations is one of the most classical problems in mathematics. We have already addressed this topic in Bolzano's theorem video. If we have a continuous function on an interval AB such that f takes values with opposite signs at the endpoints of the interval, then there is certainly a solution of the equation f of x equals 0 between a and b. Moreover, such a solution can be numerically determined using the bisection method. I recommend revisiting the video on this topic. Here, we present a new algorithm for numerically solving equations. This method was first described in 1669 by Newton and then progressively extended by various mathematicians, achieving this current form around the 1740 thanks to Simpson. The key assumption of the method is that the function f is strictly convex and increasing on the interval AB. Specifically, we assume that f is convex, the derivative of f is strictly positive and continuous. Now, notice that if we take the final point on the graph of the function, and in particular the tangent to the graph, which is the green line you see here, whose equation is y equal f prime b times x minus b plus fb. Well, this line crosses the axis at point x1, where the function f is still positive, so the 0 is probably at left of this x1. But with respect to b, we get now a little bit close to the solution. Now, this point x1 can be determined by solving the equation this equals 0, from which we get x1 equal b minus this fraction. Since at b the function f is positive and the derivative is always positive, this fraction is positive, and this means that x1 is effectively at left of b. Now, the intuition suggests that this is a well approximation with respect to b of the solution x star. So what should we do now? We should compute f at point x1, and we have this alternative. Either the value of f at point x1 is 0, this means that we finished our search, or since we know that the f of x1 is greater or equal than 0, because the function is above the tangent and the tangent is 0 at x1, the value of f must be strictly positive. So what we do is to repeat the search on the interval from a to this point x1. We take the tangent to the graph of f at point x1 fx1, which has equation this one, and we know that this tangent, green, is still above the orange line, which is the graph of the function f. So this means that when the tangent line crosses the axis, the function is still positive, or possibly 0. Now, the point x2 where the green line crosses the axis is given by solving this equation. So it is x2 equal x1 minus the ratio fx1 divided by f prime x1. And since fx1 is strictly positive, the derivative is supposed to be always positive, this point x2 is at left of x1. Now what we do, we compute the value of f at point x2, either we get 0, so we finished, or we get positive value. And then we continue on the interval ax2, we will get a point x3, etc. So iterating this method, what happens? After n steps, we have the following alternative. Either we find an xn for which fxn is equal to 0, then we stop. Or for every xn, f of xn is strictly positive, and we build a new xn plus 1, through this formula, xn minus the ratio fxn divided f prime of xn. Since at point xn the function is positive, the derivative of f is supposed to be always positive, this fraction is positive, so this means that we are subtracting a positive number to xn. So the xn plus 1 will be at left of xn. So if we represent points xn on the real line, we see that they are moving from right to the left. So they are any decreasing sequence of numbers, and therefore they will have a limit that we call x star. Now, our goal is to prove that that x star is exactly the solution of the equation f of x equals 0. Indeed, we take xn plus 1. Since xn goes to x star, also xn plus 1 will go to x star. It is x index n plus 1. Now, xn plus 1, because of the equation that defines points xn, is equal to xn minus this ratio. What happens here if we send n to infinity in this right-hand side? Well, xn, of course, goes to x star. Since the argument of f goes to x star and f is continuous, why? Because it is differentiable, so it is continuous, the numerator of this fraction will go to f of x star. And also the denominator will go to f prime of x star because we assumed that f prime is a continuous function. So we have that this quantity will go to f x star minus f of x star divided f prime of x star. There is no danger with this denominator because we assumed also that f prime is always strictly positive. Now the two limits must be the same, so this means that x star equal x star minus this ratio. And to be true this, it means that this fraction must be 0. But the fraction is 0 if and only if the numerator is 0. That is f of x star equals 0. And that's where we have that x star is a solution of the equation. Now let's see a nice application of this algorithm to computing roots of positive number. Now you may think, what has to do roots with solutions or zeros of equations? Well, we may think that number x is a root of y if y is equal to x squared, right? So this means that we can see this as an equation x squared minus y equals 0, where y is given, so it's a data, and x is the unknown to be found. So if we set f of x equal x squared minus y, we now apply to this f the Newton method. In fact, this f is convex. The second derivative is constantly equal to 2, positive, so it is convex. And for x positive, the derivative of f is strictly positive. So it means that on 0 plus infinity, the assumptions of the theorem we have proved a minute ago are verified, and this produces the following algorithm. So we have that xn plus 1 is, in general, xn minus the ratio f xn divided f prime. If we plug in the values of f prime, we get xn minus xn squared minus y divided by 2xn. And this yields this formula. Xn plus 1 equal 1/2 xn plus y over xn. This is a very ancient algorithm. It is in fact known as the Heron's method. And also it is known as the Babylonian method because it was found on some Babylonian table that this algorithm, this formula was written somehow, of course without any particular explanation. Now, it is interesting to notice that if we take y equal 2, so it means we want to compute the root of 2, and we start from x0 equal 2, which is larger than, this is the b, let's say, which is larger than root of 2. After just 5 iterations here, we find this value for the root of 2, which is an approximation to all these digits. Really nice, right? A dual method to the Newton tangent methods is the second method. It is still based on convexity, but it does not require the derivative of f. Now, let's see what is the idea. Take the chord joining the initial and final point. Now, we know that by convexity, the function f is now below of the green line here. Take the point where the green line intersects the x-axis, so where this is 0. Now, this can be easily found because this is the equation of the chord. If we impose that this is 0, we get this value for x1. At this point, as you see in the figure, the function will be, in general, less or equal than 0. So if it is 0, we finish. Otherwise, if it is negative, we should repeat the search on a smaller interval, that one that goes from x1 to final point B, and so on. Okay, now I hope that this video has been helpful for you. I would suggest you to try to complete the argument for the method of seconds, showing that the points xn that you construct forms an increasing sequence of points that converge to some x star, which is a solution of the equation f of x equals 0. And then maybe try to see what is the difference between the two methods on computing the root of a number y. Well, good luck.